Hi, I'm Liz. I'm a first year PhD student in astronomy, and this is my second paper review. I hope I fixed some of the issues from the last one. I think the quality of the video should be now better. Also, there was a problem with audio, I had to re-upload. So, I hope this one will be better. Yeah, so today there is going to be a review on the paper by Dullemond and Dominik from 2004. It's called The Effect of Dust Settling on the Appearance of Protoplanetary Disks. This is also a paper quite relevant to one of the projects that I'm doing right now. And it was, I have to say, it was a very nice read. It was a very pleasant paper to just the writing there, typically when you go about papers, you usually just read an abstract, skim the figures, maybe read conclusions, right? And then if you need details, you can go deeper into that. But typical strategy is like this. But this paper, even though I skimmed the figures before and found them very interesting, when I decided to review the paper, when I read the abstract, it was such a well-written abstract that I just continued going on into introduction and in a very, I read it like a book essentially. And yeah, I'm very excited to review this paper on this premise, and it has nothing to do with the fact that I'm collaborating with Dullemond or anything, or using his software. No. That's no. I mean, I'm saying it's like a sarcasm, but no, it's really unrelated. I really enjoyed the paper. Never mind. Don't forget about that. I'm sorry. Anyway, so what is the setup of a problem? And it's kind of based on the problem from the previous paper, just a bit earlier paper, also the paper Dullemond Dominik 2004. It just came out a bit earlier. And the problem there is that if we take SEDs of Herbig stars, we essentially see, we can group them into two types. And on the right there is a plot from that paper which has two examples from those groups. So the group 1 has in mid to far infrared, so beyond 20 micron, flux as strong as the 10 micron feature, that is more or less constant for a few tens of microns. The second group, on the opposite, has a fainter flux than on the 10 as the peak, compared to the peak of 10 micron feature, and it's declining with the wavelength. And the question is why? And in that paper they tried exploring scenarios, namely scenarios of self-shadowing, what can cause it. And theoretically, what could be the reasons for this self-shadowing are dust growth. Basically, if your dust is grown, its optical properties are different. Namely, they have reduced capacities. That means that they absorb less light. That means that they're colder. And in hydrostatic equilibrium assumption, that means their height scale is lower. So that would mean that the outer disk, which has this more grown, assuming that it has more grown dust, will be lower and can get into the shadow of inner regions, which in the case of Herbig stars, because this is disks around such massive and luminous stars, the inner rim is so hot it's puffed up. I mean, that's the assumption, and this puffed up rim can create quite a huge shadow onto the rest of the disk. And that's what they explored in that paper. They looked at different scenarios that can cause self-shadowing. I will not go into details. They did not explore dust settling, however, which is also can be the reason, and this is just a literal settling of the dust closer to the midplane. Therefore, the height scale will be smaller. Yeah. Also, this is the way how you can put dust into the shadow. But in this paper, they explore the effects of dust settling onto SEDs, but of T Tauri stars, where it should happen as well. But I suppose that at the time, they did not have such a good sample of T Tauri SEDs, mostly I suppose because of the sensitivity issues. So how big stars are huge, luminous, it's easier to observe them. And with T Tauris, I suppose that, I mean, there must have been some SEDs, but I suppose that they're mostly from group 1, which are more luminous, and therefore there was some kind of observational bias. And it was mostly like interesting to predict like if dust settling is going on in T Tauris, how the SEDs would look. So further on in the paper, they have quite a number of like analytical derivations and stuff. I will, in this paper review, I will avoid the formulas because I just feel this way. And I will just explain the idea behind this thing. So settling, first settling. So if, in theory, if your dust is orbiting a star and there is no gas and it's above the midplane, it will just go about its merry way on the Keplerian inclined orbit, right? Nothing should happen to it, it will just round and round about. But if you have gas, when dust reaches the gas rich area, and it will cross the midplane twice a year, it will start experiencing friction against that gas, and that would make it lose momentum and bring its orbit closer to the midplane. And this is an effect that slows down towards the midplane because, well, the gravitational component, Z component of gravitational force onto the grain decreases closer to midplane, and also there is a higher gas density and it's more effectively stopping the grain, and therefore the speed, the velocity of settling decreases. And in theory, if that would be the only process, then all dust at some point would just settle onto the midplane and stay there in an absolutely thin disk. However, there is also turbulence in the disks that can yank up these dust back to back up. Yeah, shouldn't be another word. And this is an effect that is stronger closer to the midplane because you need sufficient gas density for it to effectively pick up the dust and bring it up. Therefore, this is two effects that go against each other and have different strengths in different areas. So settling is stronger higher up, stirring is stronger closer to midplane. Therefore, there must be some kind of equilibrium that will define the vertical distribution of dust density. And basically this is what they find through this analytical formulas. And here is the plot for these analytical solutions. So they and this is these estimates are made using a very simple model of the disk. So it's just assumed to be the surface density is assumed to be according to the power law, not even tapered. The temperature is also derived analytically from just considering heating by star and cooling by thermal radiation. Also, I think there is an assumption of a thin disk, and for vertical structure there is just an isothermal hydrostatic equilibrium. So all the most primitive way you can describe a disk, it's that. And here's the results for the positions of Z depletion versus radius. So basically, what is this value, Z depletion? This is a solution for, this is, no, let's say that another way. It's the height at which the time scale for settling is 100 times less than the time scale for stirring. So it's where the stirring is so ineffective compared to settling that there is no dust left. So all the dust for, so the line, this is the line for, the lines are for different dust sizes, and it means that all dust must be of that size, all dust of that size must be below this line. This is like on this, on the line itself, there's like zero dust of this size, nothing. Also, there is a tau equals 1 surface. It's at the wavelength of 0.55 micron, so green light. And it's calculated assuming like initial distribution before settling. So like when dust is considered to be well mixed with gas. So this is kind of a reference line. And there is two turbulence parameters, alpha and Q. Alpha is essentially equated to the accretion alpha. So this viscosity parameter from Shokuro-Sunyaev alpha, essentially. And yeah, so what do we see here? There are two things that they take away from here. Is that for some of the dust sizes, you see that this line at some point decreases with radius. So this is like kind of a hint at the possibility of self-shadowing, right? Also, for tau equals 1 surface, there is a note that so on this wavelength, the opacity is dominated by dust around 0.1 micron, and it's above tau equals 1 surface, so it's not really influencing it at this alpha parameter. On the right, there is a plot of settling time scale. So basically how much time it requires for dust of this size to settle into a steady state equilibrium. And so it also depends on the size, yes, and larger sizes settle quicker, and all of the sizes settle faster than the accretion time of the disk. So basically this is an estimate of the lifetime of the disk, essentially. So the conclusion here is that dust has enough time to settle before the disk accretes onto the star completely. Okay. Then these are the same plots but with alpha parameter 100 times less. So it means that the turbulence is 100 times weaker, and that leads to more effective settling of the dust. And in this case, now we have this 0.1 micron dust, completely non-existent at tau equals 1 surface. So there is no 0.1 micron dust, which means that settling should affect this tau equals 1 surface. Also, if we look at settling time scale, well, it's longer, but it still holds that it all has time to happen before the accretion occurs. And also, at smaller radii, so in the inner part of the disk, the settling is faster than in the outer part of the disk. Okay. Oh, and also this plot, so there's also settling time scale, but not to the steady state, but for going below the tau equals 1 surface. And I suppose it's so you shouldn't look at, it's not for Z depletion time scale, it's more like for kind of a majority of the dust. So so don't compare those two, because for some dust they never go below tau equals 1 surface. So so it's not for these surfaces, it's just a different parameter. Just you could imagine that like when most of the dust goes below the tau equals 1 surface, and most of the dust sizes have enough time for it to happen before the accretion time scale, except for the smallest dust in the outer regions. Okay. So that's for steady state, right? But the authors decided to then explore it on more dynamical. They wanted to see how the dynamics of this process, and so they come up with a differential equation that would describe it, and then started solving it. And here on this plot, this is a plot of dust to gas ratio at different heights at 10 AU. So this is the result of this solution. And there are results for a different years. So 1 year after, 1 year before, no, at 1 year this is this constant line. So this is a well-mixed, who wrote to me? Never mind. A well-mixed gas with dust at a constant 0.01 ratio. Then you turn on dust settling, and it happens rather quickly and very sharply. Basically, like if you consider, what is it, 1,000 years in, you have nothing above that that height. This is what they note. And the reason for it being so sharp is that because the velocity of settling decreases as you get closer to the midplane. Therefore, kind of the dust from upper layers catches up with the dust from the lower layers, and they kind of all move together as one wall. But as they near the stationary state, of course the stirring starts to play a role, and it kind of smooths out into this distribution that is stationary solution. And on the right you can see basically where, at which heights timescales are equal, so the Z settling. This is where the stirring and settling timescales are equal. And the Z depletion that is from the previous plots, this is where the stirring timescale is larger than settling by 100. So basically when stirring is ineffective completely, and this is where you don't see any dust. Then they do that on a number of radii, not only 10 AU, and construct SEDs simulate SEDs from this result. And what we see here is that there is, after 10 to the 5 years, going to 10 to the 6, there is a very sharp drop in luminosity, and you see that how essentially from this group, if you remember these plots of SEDs for Herbig stars, it goes from group 1 SED to group 2, which kind of suggestive, and this sharp abrupt drop is kind of suggestive of self-shadowing happening. And you can see it also here on this dependence of scattering intensity on the radius. So initially it goes like this, then as dust starts settling, it does that very quickly in the inner regions, but it does that gradually. But and you see that like at 10 to the 5 years, the intensity of scattering is pretty much as at the start for the outer regions, but then bam, 10 to the 6, it drops by how much orders of magnitude? A few orders of magnitude, let's say that. And then in 10 to the 7th it drops even further. I mean, okay, I know what you might be thinking, that the time scales are in like an order of magnitude more, so is that really that abrupt? But it is an indication of self-shadowing, authors argue. And this can be seen very well on this plot, which is the position of tau equals 1 line, again at the same wavelength, and how it evolves with time. So this is how it is in the start. It's very quickly in the inner region settles to its position, but in the outer region it goes to this position in 10 to the 5 years, and then in the 10 to the 6 it's this constant that starts in I think it's 7 AU. So what that means, if it's a tau equals 1 surface, and this is for, by the way, all these tau equals 1 surfaces are computed from for stellar radiation. So basically it goes like along the horizontal lines. So this means that whatever matter there is, it's mostly below that height. It's hidden behind this inner part. And this is self-shadowing for sure. Then they do it again, but now they consider, instead of one dust size, here they used just one dust size, sorry, I forgot to say that, which is 0.1 micron. But here they use a whole size distribution, which is a standard one size distribution, MRN size distribution, so from 0.005 micron to 0.25 micron. And what we see here, and this is what's surprising to them, is that we see absolutely the same type of, well, not really surprising, but interesting, that we see The same kind of behavior here as well, and we see this group 2 self-shadowed SED shape as well. And they find it interesting because what they see in the model is that small grains are still quite high up. They still have not settled. Larger grains, yes, have settled, but smaller, no, they're still up in the atmosphere there at larger radii. And they explain it by, well, yes, but it's just that they don't really add anything to absorbing and re-emitting emission. Yeah, I'm re-emitting emission. Light. I don't know. You got me. Okay. Never mind if I sometimes make awkward phrases. You got me. You know, the smaller dust that stays high up does not really contribute to SED at this wavelength. It is done by a dust, I think they say around what? Let me just make sure real quick. Yes, 0.03 micron. So because most contributors here are dust more than 0.03 micron that has settled, that still happened despite those smaller dusts still up there. And we see something similar to that one size case, and self-shadowing still going on, though at a bit smaller amplitude. And for scattering, we see actually also a much stronger effect, because what happens is that is that even though on the larger radii, no, wait, God, so embarrassing. What was the explanation? Yes. Yes. So it's because in addition to large grains settling, smaller dust on the closer to the star radii have not settled as much, but they're not reflective, but they can still extinct the starlight that's on the way to reflective dust on larger radii that may not have, actually settled that much yet, and that kind of decreases their reflective ability because of this little bit extinction on the way. So it's kind of this an effect of different timescales for different dust sizes working here to decrease the scattering intensity. And this is tau equals 1 line. Also quite similar to what we've seen before with one dust size, but there is a bit of a smoother transition here. And I think it's not completely constant, like this stationary structure. It's like going up a little bit, but it's still very close to, like, it's essentially self-shadowed more or less as well. So we still see self-shadowing here. And this is like a little cherry on top figure of simulating an image again at the same wavelength, 0.55 micron, at different years for the Summerend size distribution. And you see that with time, like initially you see the entirety of a disk reflecting the starlight. Star is kind of picked away out of here. It's kind of an ideal coronagraph. But with time it becomes less and less bright, and it tends to this, like in 1 mega year, essentially your disk is self-shadowed and doesn't reflect any light, and you don't see it anymore. And now discussion. So let me just pull up my notes. I should have prepared that in advance. So what do they discuss? So first of all, they talk about viscous heating. They don't include viscous heating. But so how would it change the results? It's well, essentially an additional source of heating besides the star, and it should be important for inner disk, for heating up inner disk. But as they show on the estimates, it doesn't really concern the outer disk. But heating up the inner disk can increase the scale height there, and that can potentially increase shadowing. So yes, that's the effect that they haven't included, but that might be worth considering. Then section about geometry. They say that, okay, why this is like, this sketch is most relevant here, is that in their previous paper for Herbig stars, they had a puffed up inner rim creating this shadow that the disk kind of falls behind. We don't have it here because it's T-Tauri stars, they're less luminous. They are assumed not to create a puffed up rim, or at least create not such a strong puffed up rim. But it's interesting that we still see this self-shadowing happening due to dust settling in the outer regions like that. So there is no puffed up rim, but it's just the disk beyond some radius just settled so much that it got self-shadowed. Also, another thing that they mentioned before discussion, but I thought to include here, is that, so in this consideration, they don't really change the temperature. They prescribe it on the very, like, initially, and that determines the vertical structure from hydrostatic equilibrium. But this change in structure should lead to a change in temperature, and for SADs they calculate temperature for this new subtle structure, but they don't change it, but they don't investigate the effect of it on the disk structure. But it should have, because if you consider hydrostatic equilibrium, it should decrease scale height. Decreased temperature should have decreased scale height. So because the disk is self-shadowed, starts to become so because there should be like a bit of a positive feedback effect that if your disk starts settling, become less flared, dust gets less light, becomes colder, and in the assumption of that it's also, but it's anyway, and in assumption of hydrostatic equilibrium, this should lead to also smaller scale height. Though I feel like it provokes, like, because it's a bit harder than that, because in reality the hydrostatic equilibrium assumption is not for the dust, it's for the gas, because the thing that balances out the gravity is the pressure. This is where this hydrostatic equilibrium comes from, and it's for the gas, it's not for the dust. Dust doesn't really interact with each other because there's not enough for it to interact like a gas. And so it changes dust temperature, and it's the question, how does the gas temperature evolve then? So to do a very to do a much more careful consideration of this, you need to kind of consider how this dust temperature is transferred to the gas when they are decoupled, because here they do effectively become decoupled, because it's only the dust that is settling, not gas. Yeah, and it should affect the thermal balance, and potentially it will also impact then the whole settling process, because it's because it depends on the gas and how it's distributed. So yeah, that's a heavy link. That's a separate thing of its own. They did not consider this, but yeah. Then another thing is that, also in the previous work with Herbig stars, they have explored this self-shadowing through dust growth, right? That was essentially coupled to the gas, and that's why a change in the dust temperature led to the decrease in the scale height. And so in theory, actually, both should happen in both Herbig and Titauris. And what we actually should see is not just this dust settling effect or dust growth effect. Both should be present, and there should be some kind of combined effect onto the disk structure, and that warrants different research, I suppose. Maybe someone has done it in this 20 years, probably did. I don't know. Would be just to find out. And lastly, they talk about timescales, and the thing is that they find them to be fast. And with these timescales, what they should see is that sufficiently old disks should be self-shadowed, and we should see it in SEDs. And I suppose that at the time of the publishing of the work, they did not really see it, I suppose because of observational bias. Right now, I can say that there are samples of Titauri SEDs that show the same level of diversity as the one that was on the slide of introduction for Herbig stars. So I suppose if they did not, and I don't know this, if they did not see Titauri SEDs that were like group 2 declining in the far infrared, then basically this paper predicted those SEDs in Titauri stars, and actually, in that sample that I'm thinking of from the paper by Shin et al. 2023, there's, I think, majority of the disks, and they're all, I think, Titauris there, have this declining SED as if they're self-shadowed, and the ones that have like SEDs like group 1 are more in minority. So I think that it's more or less in agreement, I suppose. So yes. So the conclusions. So dust settling can change SEDs on timescales of 1000 years for smaller radii and 0.1 megayears for larger radii, whilst equilibrium is achieved at 1 megayear. And this is obviously alpha dependent statement. I think this is based on 10 to the minus 4 alpha. Then settling at larger radii leads to a self-shadowing of the disk, like presented here. And these disks show a much weaker mid to far infrared excess in SED and are essentially undetectable in reflected light when we compare this to flared disks. So a very interesting investigation. I very much liked reading this paper, and this is kind of a problem that I struggled as well. I'm kind of trying to model inner disks and observations of them, SEDs of them, and with assuming hydrostatic equilibrium only and coupled gas and dust, basically that dust is wherever the gas is, just 100 times less mass, I do get this mid to far infrared excess and the objects that I'm trying to fit do not have it. I mean, they have much less of an excess. I mean, all class 2 disks have this excess, but it's just smaller in the self-shadow disks. And I found it to be it's impossible to fit it without dust settling, and I've been exploring how to do that, and basically this paper is just telling me that yes, this is the way to do it. I look at this plot and I'm like, yes, this is what I need. So I will be implementing kind of a steady state solution from this paper. There are a number of other papers that do have they're all quoting De Bruyne et al. 1995, which has this steady state solution that links scale heights of gas and dust. But I will try the one from here. Oh, I don't have formula anyway. Yeah, whatever. But basically it is based on taking this Z settle from that graph, this solution, and taking it as a scale height for dust. And there is a link to a scale height for gas. So I will try that. I'll see the results. I hope it will give me something satisfactory, but yeah. This is it. Thanks for listening.